Hello everyone, I'm Dr. Mohsen. In the course of remote sensing and GIS, today we will discuss about the digital image processing. So let's start with the introduction of image processing. What is image processing? It is an enhancing an image or extracting information or features from an image. Computerized routines for information extraction, for example, pattern recognition, classification from remotely sensed image to obtain categories of information about specific feature, and many more. Image processes include image quality and statistical evaluation, radiometric correction, geometric correction, image enhancement and sharpening, image classification, pixel-based or object-oriented based, accuracy assessment of classification, post-classification and GIS, and then finally change detection in the final processed image. Image quality. Many remote sensing datasets contain high quality, accurate data. Unfortunately, sometimes errors or noise is introduced into the remote sensors data by or due to the environment, the atmospheric scattering or clouds, random or systematic malfunction of the remote sensing system, or the improper preprocessing of remote sensor data to prior actual data analysis. So here the image collected from the Landsat enhanced thematic mapper plus ATM plus. The red circle shows the cloud cover, and here in the process image you can see the presence of cloud in the white color on the image. So what is behind these clouds? These are the errors that can be removed with different process. Stripping noise and removal. So combined principle component analysis is applied to remove the noise, and you can go and for the detailed study the Zayat alt 2004 paper. You can study it for the further exploration about this method. Speckle noise and removal, blurred objects and boundaries. So GMAP, gamma maximum filter is used to clear these boundaries and images. Radiometric correction include detector error or sensor error. These are the internal error, atmospheric error or also known as external error, topographic error or the external error. So what is the atmospheric correction? There are several ways to atmospherically correct remotely sensed data. Some are relatively straightforward, while others are complex, being founded on physical principle and requiring a significant amount of information to function properly. This discussion will focus actually on two major types of atmospheric correction. The first one is absolute atmospheric correction and the second is relative atmospheric correction. So absolute atmospheric correction, solar radiation is largely unaffected as it travels through the vacuum of space when it interacts with the Earth's atmosphere. However, it is selectively scattered and absorbed. The sum of these two forms of energy loss is called atmospheric attenuation. Atmospheric attenuation may be or may it difficult to relate handheld in situ spectral diameter measurements with remote measurements and make it difficult to extend spectral signature through space and time and have an impact on classification accuracy within a scene if atmospheric attenuation varies significantly throughout the image. But the main aim or the general goal of the absolute radiometric correction is to turn the digital brightness values or the digital numbers recorded by a remote sensing system into scaled surface reflectance values. These values can then be compared or used in conjunction with the scaled surface reflectance values obtained anywhere else on the planet. So here's the absolute atmospheric correction. The left image presents the before atmospheric correction, and the right side presents the after atmospheric correction. Relative atmospheric correction. When required data is not available for absolute radiometric correction, we can do relative radiometric correction. Relative radiometric corrections may be used to single image normalization using histogram adjustment or multiple data image normalization using the regression technique. Topographic corrections is a topographic slope and aspect also introduce radiometric distortion, for example, area in a shadow. The goal of a slope aspect correction is to remove topographically induced illumination variation so that two objects having the same reflectance properties show the same brightness value or digital number in the image despite their different orientation to the sun's position, or based on the digital elevation model or the sun elevation. Backscatter distortion, so the geometry or the local incidence angle also matters. Theta prime is less than equal to theta in the first case, and the second theta prime equal to theta, and the slope is like this with the satellite, so theta prime is greater than theta. Geometric correction, in which the geocoding or the geographical referencing registration geographically or non-geographically no coordinate system, and this image to map or ground geocorrection. The correction of digital image to ground coordinate using ground control points called collected from maps, topographic map, uh, or ground-based GPS points. Image-to-image geocorrection. Image-to-image geocorrection involves matching the coordinate system or column and row system of two digital images with one image acting as a reference image and other as a image to be rectified. Spatial interpolation from input position to output position or coordinate. So in this rotation, scale and transformation or RST, polynomial or triangulation. Intensity or pixel value interpolation, also called resampling, the process of extrapolating data values to a new grid, and a step in rectifying an image that calculates pixel value for the rectified grid from the original data grid nearest neighbor at the cubic form. Spectral ground truthing as performed in the field spectrum with using field spectrometer. Image enhancement includes image reduction, image magnification, extraction, contrast adjustment, band rationing, spatial filtering, Fourier transformation, principal component analysis, texture transformation, and image sharpening. In image interpretation, tone and color, a band of electromagnetic radiation recorded by a remote sensing instrument can be displayed on an image in shades of gray ranging from black to white. These shades are called tones and can be qualitatively referred to as a dark, light, or intermediate. Humans can see 40 to 50 tones. Tone is related to the amount of light reflected from the scene in a specific wavelength or interval or the band. Tone and color, three different types are presented here. Image interpretation, texture. Texture refers to the arrangement of tone or color in an image. It is useful because earth features that exhibit similar tones often exhibit different texture. Adjective include smooth, uniform, or homogeneous, intermediate, and rough in coarse or heterogeneous texture. So here is the texture with different tone and colors. Image interpretation. Pattern is the spatial arrangement of objects on the landscape. General description include random and systematic, natural and human-made. More specific description include circular, oval, curvilinear, linear, radiating, rectangular, and etc. So here is the example of pattern of the objects and the images. Image interpretation, height and the depth. Shadow can often offer clues to the height of the objects. In turn, relative heights can be used to interpret objects. In a similar fashion, relative depth can often be interpreted. Description include all, intermediate and short, deep, intermediate and shallow. And the height and the depth of the different pictures presented here. Image interpretation association. This is very important when trying to interpret an object or activity. The association refers to the fact that certain features and activities are almost always related to the presence of certain other features and activities. Here are the association with the presence of different other parameters. Multispectral and hyperspectral images. Number of spectral channels. In human channel there are 3 color RGB. Most mammals very limited color vision. Crab 6 color. Bird up to 7 color, up to 8 times the resolution of human eye. Monochromatic, panchromatic, multispectral, hyperspectral and ultraspectral, and their ranges are given here. Multispectral remote sensing is defined as a collection of reflected, emitted or backscattered energy from an object or area of interest in multiple bands of electromagnetic spectrum. Instead of cameras and 1 to 4 bands of photogrammetry, remote sensing uses detectors that are sensitive to from multiple bands to hundreds of bands in the electromagnetic spectrum. Measurements made by detectors are always stored in a digital form as HDF, BSQ, BIP, or BIR. Multispectral sensors are Landsat, thematic mapper, enhanced thematic mapper, spot, HVIR, vegetation, HRs. In hyperspectral, many remote sensing systems recorded energy over several separate wavelength range at various spectral resolution. These are referred to as a multispectral sensor. Uh, Advanced multispectral sensor called hyperspectral sensor detect hundreds of very spectral bands through the visible, near infrared and mid infrared portion of the electromagnetic spectrum. Hyper are the narrow bands less than 20 nanometer in resolution and continuous measurement. Imaging spectrometry, the simulation acquisition of image in the many relatively narrow, contiguous and or non-contiguous spectral bands throughout the ultraviolet, visible, and infrared portion of the spectrum. The very high spectral resolution facilities fine discrimination between different targets based on their spectral response in each of the narrow bands. Here the hyperspectral, collecting detailed information for the whole electromagnetic spectrum. Hyperspectral explanation of spectrum information by standard multispectral sensor. Number of spectral band 3 to 7, width is 80 to 200, and it's as scientists many bands with width of 10 to 40 nanometer. Here the hyperspectral concept. Each spatial element has a continuous spectrum that is used to analyze surface and atmosphere. 24 spectral images taken simultaneously. Hyperspectral sensor Aster, MIS or EOS Terra, and the MODIS is the example. If you have any question, you can ask me through the group, and we will discuss in detail on the Google Meet when we will perform some practical work also on the GIS and radars and other systems. Thank you very much.